Okay, sorry about that. Whoops, echo. Alright, can everybody hear me? Sorry, a little late, I had to reboot. Okay, perfect. Yes, thank you, Jenny. Always give me a week to get back to you about the test. I grade question per question. So I already graded the first two. I don't know how many there is, but I'll try to grade as many as possible every day. I'm usually always on time, unless something pops up. So at the latest, next Monday, you should have the grade. And then after that, you're more than welcome to stop by my office to pick it up. Well, it's difficult to say when you grade question per question, but the second question seems to be okay, which is good. The first question seems to have a lot of problems, so I will keep putting vector problems on quizzes and on further tests, because it seems like we need to practice more. So, today's what? Wednesday. Okay, so let's keep going our journey on Newton. You've continued to work out the problems and hopefully completed the NA series by now. So how did everything go? Is there any questions on any of the NA problems? NA5, NA6, NA7, NA8, NA9? If you're already caught with those and you started the E series, is there any question on the E series? Of course I will. NA8. Excellent, thank you. I was going to do a composite anyway. I was debating whether it would be a 7 or 8. Since you asked for 8, thank you, let's do it. So, 8 wait, I'm sorry, let me bust up the diagram. Where are you? Where are you? Sorry, I'm being challenged to find the problem. Almost there. Okay. Okay, so we have two little buggers connected to one another by a vertical spring, and then the top one is connected to the ceiling. They are given us both weights, both masses, MA and MB. We're being told that the string is massless, so we don't have to worry about its mass, and they don't stretch, so that's good. Block A is also going to get put to the ceiling, but another massless. Okay. Okay, they're just sitting there initially. So obviously, both system A and B are at equilibrium. Calculate the tension between the two blocks. Okay, so Jamie, since you asked for it, how did you start? For example, since we know the first step is to identify our system, which system did you pick? Oh, I thought you asked for it because you worked on it. Oh, okay. B, so can I say, well, let's do B. Okay, we can do B, it's a free country. What else can we do? Yeah, excellent, we could do A. So we could either do A or B. Sometimes we have no idea which one. Doesn't matter, just pick one. That's the great thing about mechanics. You always know how to start. We obviously are being asked to calculate the magnitude of a tension, which is a force. Therefore, Newton's analysis come to mind, and Newton's method is very clear. Pick a system and go with it. If it doesn't go anywhere, then we pick another system. Now we could pick A, or we could pick B. What else could we pick? And usually we pick massive system when we apply Newton's law. And this is a little bit of a tricky question, but what other system could we pick? We know we could pick A or B. There's a third possibility. The string is massless, so usually we don't pick that guy. Excellent, Justin. Thank you. We could pick system A and B and consider A and B as one system. So we can draw a box around A and B and ignore everything inside the box, because those are internal, and since we don't care about what's happening internally, because Newton's first and second law is asking us to identify the external forces acting on our system, then we just look at our new box that includes A and B and look at all the contact issue. So we could do that too. So I'm going to follow Kyle and Kyle by looking at A and B, but I would strongly suggest to redo this problem by considering both system A and B and make sure you get the same answer. I will just lay out the steps with both systems. Oh, okay, so we'll do, okay, give us, so let's do, well, between A and B, which one you like to do first? Which one do you think is going to be the easiest? That is, which one by first looking at them is most likely to have less external forces, therefore less algebra? B, excellent. So let's do B. We always need to find the laziest version first, because if we can get away with it, we save time and pain. So, if I do B, what are the forces, the external forces acting on B? The weight, excellent. And now here is where our label are going to be very important, Michael. This is the weight of object B. So running it out will help you remember that this M is the mass of B, not the mass of A. Okay, so please keep track of your label. The weight showing up in the free body diagram of a system must always be the weight of that system. Therefore, you can only have one weight, and it has to be about the system that you're studying. So the weight of A should never show up in the free body diagram of B, and vice versa. Good. Next one that comes to mind on the list after the weight. That's the third one, Tyson and Mallory. Which one did you skip? Normal force, thank you. In this case, our object B is not sitting on a particular surface or in contact with one of its surfaces with another object. Therefore, in this case, there is no normal force. But obviously, as we get to the third one, there is obviously tension. Because as we look at and scan the exterior of our object, ping, up, there's a rope, therefore there's a contact. Let's call it a tension. Good. Now, is this tension going to go up or down, Tyson and Mallory? Imagine that you're a bee. Would the force coming from the string attached to your head would most likely pull you up or down? Up. Excellent. Perfect. So let's call it T, and that's the tension that we're looking for. That's the tension between the two blocks. Perfect. So that's exactly what we want. T is what we want. Good. Obviously, there is no friction. Therefore, that's it. Only two forces. Well, that seems like a pretty cool problem. Nice and easy. Let's compile a coordinate system. Let's pick a coordinate system, X and Y. Obviously, T and MB are aligned along the vertical. So let's pick at least one of them on the same direction. There's no forces in the X, so we don't really care. The directions are very clear. Hence, as we apply Newton's first law, because the system are just standing there, This will give us T minus MBG is equal to 0. Hence, T is equal to MBG. So far, so good? So in this case, we got lucky. We picked the system that allowed us to get the answer right away. Good. If we were not that lucky, sometimes we pick the wrong system. So let's keep doing this problem, but let's pick a different target. And before we get to Justin's suggestion, let's pick A, just to see what happens. If we pick A as our system, similarly, we're going to get MAG. What else is going to be present? Obviously, no normal force, same thing as B. But how many forces of the third type is going to be present? Yeah, there's going to be 2 tension forces. One is from the string above A, which, same as the one on D, will tend to bring A up. Let's call this T prime. And then there is a tension due to the object B. This one. Is this tension acting on A? It tends to pull object A down or up? Down, excellent. And how are you going to call this force? T2, excellent. We cannot make any assumption at this stage. Even though in this case we're going to see it's trivial, no worries. Let's give it a different name. Okay, so now let's look at the number of unknown that we have. How many unknown do we have as we do object A? How many of those variables don't we know? There's 3 forces. How many are unknown? 2, T prime and T2. We know MAG. How many equations can we write from Newton's first law? How many scalar equations? 3. So that means we're dealing with a 3-dimensional system. There are forces in 3 different directions. 2. So that means there are forces in 2 different directions. Look at the direction of your little vector. Yeah, only 1 in this case, only y. So we only can write 1 equation. But we have 2 unknown, T prime and T2. So we know that if we never went through B and we start at A, we can never solve for this problem. The only equation we can write, and as we apply this technique, we will end up with this, would lead to an incomplete solution. That's okay. If we never did B and started at A, and I realize, whoops, I know that if I do analyze A, I will end up with 1 equation, and I will be facing 2 unknown. That's okay. All you have to do is pick another object afterwards, and keep doing this until the number of unknown matches the number of equations. Always do that. Never start writing equations, combining them, unless you know for sure that the number of unknown matches the number of equations. Or at least is less. Otherwise, mathematically, you can never solve it. Now, let's do A and B before we combine and shine more light about T2, which is still unknown at this stage. And plus, as far as I'm concerned right now, object A is useless because what? Where is my tension? What am I looking for? Okay, so let's do that before A and B. The problem is asking us to calculate the tension between the 2 blocks. Is this tension showing up in Fibry diagram of A anywhere? Because if it doesn't, then object A is useless. But if you look at your diagram, and if you identify A, should you expect the force due to the string between A and B to show up in that Fibry diagram? That is this tension in contact with object A? Yeah. Therefore, you would expect that this tension that we looked for shows up here. So where the heck is it? It's T2. Thank you, Justin. T2 is what we're looking for. Now, how do you know that T2 is MBG? Excellent. And how do you know that? Because all I know is T is equal to MBG. Thank you. Excellent. That's where we're going to use Newton's third law, action and reaction. Remember, Newton's first and second law are applied to our system. Newton's third law is always applied between systems in contact. So the force acting on B from A, which we call T, is the same as the force acting on A from B, which is T2. So usually with practice, what we usually do is we don't give it a different name. We recognize directly that this is where the third law is applied, therefore we give it the same name. Yes, Justin. Okay. So when two systems are in contact, this is where we apply the third law, right here. The third law is never applied to one system, only the first and second. The third law only shows up when two systems are in contact with another. In this case, A and B. So the Newton's third law, by definition, tells us that the force of 1 into 2 is equal to negative the force of 2 into 1 in vector. So let's apply this. In words, it says that the force applied on B by A, which we call T, which is up, is exactly the same in magnitude as the force applied on A from B, which is T2. So they have the same magnitude, but they have the opposite direction. And since we put the correct direction in our free body diagram, we can drop the subscript. Hence, at this stage, you're welcome. T2 is just T, and that's what we're looking for. Can you write that out for us in equation form? Oh, you mean the definition? This is Newton's third law in this particular context. Usually the general one is using 1, 2, 2, 1. In our case, it would be A on B and B on A. Like that. So every time you look at a system and you realize that there is more than one system that you're going to have to consider, you know you're going to have to use the third law. WI people, remember that, because that will be one of the question method that I'm going to ask you. Which law or laws are you going to use in this problem? It's either going to be just the first, or just the second, or the first and the third, and or the second and the third. And you always know if you have to use the third if your problem involves more than one massive system all the time. Perfect. So again, even if we recognize Newton's third law and we call T the right way, that refers to what we're looking for, we still don't know what T prime is. T prime is the tension between A and the ceiling. So just doing A, we're toast. But then now if we happen to start with A and realize, okay, we have two unknown, one equation, let's pick another object, we pick B, and then B gives us the answer right away. So we don't even have to use T prime. So pretty much doing the analysis of Newton on object A is useless in this particular case. Now the third option, Justin, let's imagine that we're going to consider A and B together. So the easiest way is to draw your system that includes both and ignore everything inside. We're only going to be concerned about what is in contact with this new imaginary object. First one that comes to mind is the weight. Now the weight of the whole thing is the sum of the weights, MA plus MBG. What is the other contact force acting on our system A and B as you look at it, the purple? Anything else? Or is it just levitating and cruising in the air? Yeah, tension. This one. Now, which tension is it going to be? Excellent. That's going to be your T prime. That's the one. So again, as we pick a coordinate system, we pick, say, y up, x right, then we can write T prime is equal to MA plus MB. Oh, I'm sorry, I'm skipping the steps. Is equal to 0. Okay, so now if we didn't see B and we did the analysis on A and then on B, okay, now we can combine those two equations and we should get the same answer as we did for B. Do it in your head. Obviously, if T prime is equal to the sum of the weights, you plug T prime right here. The MA weight is going to cancel out. And therefore, you will be left with MBG, which was our answer. So, as you can see, it doesn't matter which system you pick. You're always going to get the right answer. It's always easy. Okay? The other very important thing about object A and B is that T never showed up, because T is inside our system A and B. Therefore, the tension T is internal to the system that we chose, that was A and B. Hence, since the tension T is internal to our system A and B, it cannot show up in our free diagram that only includes external forces acting on our system. So the wording is very, very important in physics. Not only in classical physics, but even more important in quantum mechanics. People have been scratching their heads, and they still are, about how to use words to describe quantum effects. And the bummer is they realize that the word that were used in classical physics, when they tried to use the same word to express something in quantum mechanics, they were like, oopsie, oopsie, don't work. Can't use that word. I remember I was taking a class, my first class in quantum mechanics. And we started the atom. So, you know, all those stupid energy levels. Boop, 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 boop. And we started a chapter. The teacher said, from the whole chapter, there is one word that you cannot pronounce. There is one word that never can be applied to an atom. And if you say it, I'm going to kick you out of the class. And the word was trajectory. He refused to allow us to use the word trajectory as we think about the electron around the atom. So that's one example in quantum mechanics where meaning of words, or words that have meaning in classical physics, lose their meaning in quantum mechanics. And of course, my buddy, just to achieve, he was, you know, serious, he said a word, and sure enough, he got kicked out, which was fun. Anyway, any questions on this? Who asked for Jimmy? Is everything okay so far? I believe that was you asked that problem. All right. Second part. At semi-cylinder, the string connecting the two blocks break. So this string breaks. What are we going to be facing? Okay, can you give me a keyword in here? Yeah, thank you. Free fall. That's it. Free fall. Now, MB is bigger than MA, so that's good. Okay, good. Exactly. The answer is just T. Remember, we've done this last time. Excellent, though. That's exactly what it is. So even if you apply Newton on this particular system, you're going to end up with A is equal to G. But otherwise, just use the definition of free fall. And if you really want to do the math and you have trouble, go back to last Monday's collaborate session. We did it, except our system was just one mass. Now we have two masses. That's okay. You're going to cancel any one on both sides of the equation. Excellent. Excellent, excellent. So that's good, because now I can add another question by saying that there is a floor located at a distance of 5 meters and ask you what is the velocity of system A and B right before B hits the ground, for instance. And by then, you're going to be like, bah, bring it on, kinematics, easy. I can do that. Okay? Questions on this? Any problem? Any 8? Yep. That's the idea. Because remember, you're going to have a kinematic problem until the end of the semester. You cannot forget your kinematics. It's always going to come back. So we're going to build upon every chapter as we go along. Every test is cumulative. All right. So then let's move on to equilibrium. What's E1? Oh. What's E2? Ah, well, better. Let's do E2. Where are you? Where are you? Huh, I don't have you either. Okay, let's create you. E2. All right, so we have an object on an inclined plane with a given mass, 4 kilograms, and it's sitting at rest on an inclined plane whose direction is 35 degrees with respect to the horizontal. Okay, so what is the keyword here? Sitting at rest. Therefore, we know right away that the system is at equilibrium. Therefore, we're going to use Newton's first law. Perfect. What are we looking for? The normal force and the tension. Okay, boom, 2 forces. Let's apply Newton's first law. Okay, so let's identify this little bugger as our system. What are the external forces acting on this? Excellent. First, we have the weight. Then we have the normal force. Normal force comes from the contact between our system and the inclined plane. Therefore, that normal force is perpendicular to that plane, but it also acts on our system. Therefore, it has to go up. Sorry, I'm sorry. I did cut off. Sorry. Oh, wait. So where? Oh, thank you. So after we have identified all those forces, I just remodel it and move all those forces from one point. And the reason why I did this is because we have 2 angles. And angles always drive everybody crazy. So make sure that you practice those and review geometry from high school. We have an inclined plane, therefore we're going to revisit our trick from last Monday to identify where they're going to be located in our free body diagram. So this is 10. So alpha is given to us, and it's 35, and beta is given to us, and it's 10. Oh, look at that. That looks familiar. Looks like a quiz question or test questions. Even more so if I decide to pick my coordinate system like that. All right. So I have three forces. I've decided to put my veto and give you no choice on the current system so we can practice. And now we need to identify the direction of all those little forces. And I will justify afterward why I chose this one. Remember, when a system is at equilibrium, you want to pick a system such that the most amount of forces are along your x and your y. But in this case, nobody is perpendicular to nobody. Therefore, the maximum number of forces is 1. So it doesn't matter which one you pick. However, it will still matter soon. So to complete our free body diagram, what do we need? The last piece. We have our label, our forces, our coordinate system, and now we need to identify, in order to do the vector algebra, vector analysis part, what do we need? No, before that, before we are able to do this, what do we need? The first requirement of being able to express any force or vector in computation is for us to know the direction. Excellent. Not for all, Michael. Do you know the direction of all those forces with respect to x and y? Really? Only n, right? And t. No, I didn't. I just draw my x-axis. Do you see my x-axis? It's in red? No problem, no problem. Okay, so n is easy, I agree, just Jamie. And t is easy. T is defined. The direction of t is between t and the minus x-axis, so it's good. We can express this in computation easily. But mg is not. So we did this last Monday. Obviously, mg is dependent on alpha, not on beta, because beta has everything to do with the tension, nothing with the weight. The weight has something to do with the inclined plane, therefore angle alpha. So where is alpha? On the left or on the right? That is alpha between your force and the x-axis or between your force and the y-axis? You should have practiced the method we've seen last Monday and give the answer right away. Excellent. Good. Perfect, perfect. Good, good, good. Now our free body diagram is complete. Okay? Is there any question about that stupid alpha? Do we need to re-practice that method? Or is everybody okay? Alright, so now we can write Newton's first law. Obviously, in the x direction, it's t cosine beta with the negative sign plus mg sine, and that's equal to 0. And on the y, t sine plus n minus mg cosine. Again, this is back to chapter 2. We cannot lose any time to go from this point to this point. Bang! Easy. How many unknown? We have t, we have n. 2 unknown, 2 equations. No problem. Now we can start for t. Let's do it together this time. T is going to be equal to mg tangent alpha. And then we're going to plug t in the second equation, solve for n. Therefore, n is going to be equal to mg cosine alpha minus t sin alpha. And t sin alpha is mg tangent alpha. I'm sorry, sin beta. Oh! What am I doing? Nobody's stopping me? Good thing I did the algebra. Let's do it again. T is mg sine alpha divided by cosine beta, 2 different angles. Let's plug t here and solve for n. N will be equal to mg cosine alpha minus t, which is mg sine alpha divided by cosine beta times sine beta. That's easy. We can plug numbers for t and n almost. We can factorize mg cosine alpha, and we can combine those two, minus sine alpha tangent beta. and that's in Newton as well. Good. Better be both positive. All right. Questions on this? So then let's redo this. Let me erase the algebra. Take a screenshot if you need to. Let's leave those equations here. But now I'm going to redo the same problem by picking a different coordinate system. The answer should never matter. I have my angle, alpha, I have my weight, I have my force N, and I have my force T. Okay, let me pick a coordinate system standard. Y and X. Now my question is, how many directions do we need to identify now? 3, well, almost 2, right? Because the weight is easy, right? Tyson, the direction of the weight is trivial. It's already excellent. Yeah, it's already along the Y. So really, we have to identify 2 directions now. Just because of that choice, we have to already do more work. We have to identify the direction of N and T, because beta is not defined from T and either X or Y. So let's start with the easy one, N. N is the normal force. The normal force is always connected to its source, which is the inclined plane. And the inclined plane is defined with respect to alpha. So guaranteed, the normal force depends on alpha. So question for champion, where is alpha? Is it left or is it right? Is alpha between N and the x-axis or between N and the y-axis? Do, 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 do. Take your time. Justin suggests the X. Mallory confirms. Adrian confirms even more. All right, perfect. So that must be good. Ready? Is it me who have a brain fart? Okay, let's just to make sure. Maybe I'm wrong. Let's use the method. N is our vector of interest, or vector or direction alpha is between those 2 lines, right? So those are the 2 lines of interest. Let's start with the force that we're interested in and ask ourselves, is this force perpendicular to this line that creates alpha or that line? In other words, is my force perpendicular to the first line that creates alpha or the second line? First, Justin, Mallory, Adrian, do you all agree? That this normal force is perpendicular to the first line. Excellent. It not only looks like it, but it has to, because remember, this line is our inclined plane, and the normal force is perpendicular to the inclined plane. So just by the property of the normal force, we know that this N is perpendicular to that line. It's a physical property. Good. So let's ignore that line. Let's focus on the other line that creates our angle alpha. And the second question is this new line perpendicular to our X or our Y-axis? Y-axis, excellent. Therefore, alpha is between our force and the Y-axis. Does that make sense? So always go through that 2-step process. Because sometimes it's tricky to figure out those stupid angles. But with this method, you're never going to get it wrong. Easy. Does that make sense? Everybody's good? This will come back over and over and over for the rest of the semester, and in 270 and in 671. Okay, so make sure you write down those 2 steps, same as last Monday. First, you ask yourself, is the force that you're interested in perpendicular to the top line that creates the angle or the bottom line? An angle is always created by 2 lines intersecting. So identify those 2 lines and ask yourself if your force is perpendicular to the first one or the second one. Once you have identified one of the 2 lines, and there will always be one of the 2 lines, then you ignore it. So for us, N is perpendicular to the first line. Let's ignore that one and focus on the second line that creates your angle. And now all you have to do is ask yourself the second question, is this remaining line perpendicular to y or ux? If the answer is y, then your angle is between your force and the y-axis. If the answer to your second question is x, then the angle is between your force and the x-axis. So it's a 2-question or 2-step process. Excellent. That was the whole idea. It needs to be simple. Good. Now next one, we need to identify the direction between t and either y or x. Which one do you see and what is it? You can go either way, because remember, you can decompose your vector through 2 different right-angled triangles. I'm going to give you, okay, so Michael, you're going after your force and the x-axis? All right. Michael has seen this. Perfect. So remember those. Those are the same, those are the same. This. Then what else? These are the same as well. All those configurations, you wouldn't need them. The last one that we've seen is the one we just practiced, but this one is trickier to see. That's why we have this 2-step process instead. But those usually are easy to identify. That's the case here. Thank you, Michael. So obviously alpha is the easy one to identify. Therefore now we got the total angle between t and x. That's the one we're going to use. Hence our 2 equations are t cosine of alpha plus beta minus n sine alpha is equal to 0. And then t sine alpha plus beta plus n cosine alpha minus mg. Okay? So, which set of system do you like best? This one or that one? First or second one? They should both give you the same answer. So make sure you try them out. Obviously the first one. So as we've just seen, the simplicity of your equations depends entirely on the choice of your coordinate system. So always be clever. So remember the general rule. As you pick a coordinate system, you have 2 situations. First, you're at equilibrium or you're being accelerated. And as you're at equilibrium, it could be both if the system is not moving or if the system is moving at constant velocity. Same thing. If you're in that first case, choose a coordinate system such that your axes are along the most amount of forces. If 2 or more forces are perpendicular to one another, go after those. If not, like in this case, or if you have more than one angle, pick a coordinate system such that the most amount of angle are defined from your x or y axis, because then you will avoid that stupid thing. And then for the case where you're being accelerated, forget about aligning your coordinate system with the most amount of forces. You want to pick either your x or your y, and its positive direction along your acceleration. This allows you, as you write Newton's second law, to have all the right-hand side positive, and one of them will be 0. That means you don't have to convert your acceleration vector into your x and y axis. So let's simplify the algebra again. Okay, so make sure you write that down also. So you have plenty of stuff that you want to write down on the side. Write it in your own words, rewatch those lectures, and then practice, 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 practice. Questions on this? All right, so that's the number 5 then. Number 5, I'm just going to go over the main step. It's a combo of the first one that we did and the one we just did. This. They're asking for everything. The tension here, and the normal force. Again, here you have the choice. You can start with object B. If you have object B, the only forces that you're going to be considering is its weight, its normal force, and the tension. 2 equations can be written, and you have 2 unknown. So B will give you right away the normal force on B and the tension between A and B. Nice. As you do a free diagram on A, you're going to have the weight. You're going to have the tension from the other string. And I'm sorry, I skipped the normal force. Now be careful, the normal force are different. Okay, so always give them different labels. You can never assume that the magnitude of forces that you put in your free diagram are the same. The only exception is when you realize that those 2 systems are connected, like in this case, and hence you use the third law. So the third law tells you right away that this is the same T as the T that shows up for B. As you count the number of equations, again, 2 equations, Newton's first law, but you have 3 unknown, T, T prime, and NA. So if we didn't do object B, we have to pick another one. That's where just then we could pick A plus B. And in this case, the tension T will disappear. We'll have the total weight. Let's write it as total. We'll have the total normal force. Let's call it N, different from NA and NB. And then T prime. T will not show up. Okay, and then the rest is the same as what we've done. Okay, so make sure you continue and complete this problem. Now all you have to do is pick a coordinate system. Obviously for part A, T and NB are perpendicular to one another, so that's where we're going to pick your coordinate system. Second one, T and NA are perpendicular to one another, so I would pick this one. For the last one, the same as the previous problem. None of them are perpendicular to one another. So, but you realize that both alpha and beta are measured from this. So you might want to pick, whoops, Y along the N force. So the 2 angles to identify are easy. Okay? Let's practice one more time our angles. Where is 30 degrees? Between the weight of B and X or the weight of B and Y? Alright, excellent. Indeed, that's where 30 is. What about the next one? Anyone you want, Jamie. I'm just laying out the structure for this problem. But you can go and do any of the ones you like. So I just laid out all of them to show you the difference between the free diagram based on the system that you pick. But as you redo this problem, it's up to you to choose. Are you going to do A and A plus B? Or are you going to do A and B? Or are you going to do B and A plus B? Either way. Oh, I'm sorry. B. I'm going top to bottom. So now we just did B. Sorry. Let's do A. Where is 30 degrees? In the free diagram of A. And Michael asked, in the end, we need both T and T prime. Yeah, that's what the question asked on part 2 and 3. Absolutely. So part A asks for the normal force, and 2 and 3 ask for tensions, both of them. Jamie says that 30 degrees between X and T. Wait, what? T prime? This is alpha, 30? Do we agree? Or did I understand you correctly? Yeah, we finished B, right? We have all the direction. We're on A. We have to figure out all the direction on A. Where is 30? Everybody agrees it's between T prime and X? Okay, thank you. Perfect. Alpha, we didn't give them any specific name. I was asking for the angle 30 and the angle 15. So let's do 30 first. Where is the angle 30 in this particular diagram? I don't know. MGNY, Tyson say. Do we agree? Confirmed by Adrian. Perfect. Excellent. Good. Now what is the 15 degree direction? Obviously it has to do with T prime, right? Yeah. Same as last time, right? Previous problem. Perfect. Good. Nice. Now let's go to the last free body diagram, A and B. Let's identify all those stupid directions. Where is 30? M, G, and Y. Excellent. Where is 15? Same old same, right? Yeah. Done. Good. So practice this over and over and over and over, because this is where the science is. This is the physics, and it will become the engineering part as you take C270 to C271. The rest is just math, right? From here, writing Newton's equation, the 2 equation, is just vector analysis. It's just a bunch of stupid vector on a coordinate system that we need to express in component notation and add them up. That's monkey business. We have practiced this since chapter 2. Now we need to move to the fun stuff, the science. Okay? So, as you practice and apply Newton's forces on whatever problem, always pick different coordinate system to practice your vector analysis. For instance, redo the same problem and pick this, X and Y. Re-identify all your angles. Same thing here, pick this one. Re-identify all the new angles, and then write down the equations. This will allow you to not only check your answer, so you know whether you do it right or wrong, so that's easy, and it will help you practicing identifying all of stupid direction, and it will allow you to practice all the vector analysis stuff. And then once you have done this, then you pick a different one. You may want to pick this one, poof, and X over here, or call this Y and call this X. Anything different, anything that challenges you so that you can get better at it and faster. Okay, because remember, for this test, you had some questions on vector analysis, and you had 15 minutes to do so. Now you have the same 15 minutes, but you have to do more. You have to do the whole free body diagram yourself. Before it was given to you in vector analysis. We give you a bunch of forces, we give you a coordinate system, express them in component notation, add them up. That was 15 minutes. Now you have to use some of those minutes to actually do the physics, apply Newton's method, all the way to step, I forget, 3, something like that. And then you use what you've learned in vector analysis and complete the problem. Okay? So keep doing this over. The nice thing with these problems, again, is from one problem, you can create 6, 10 more. And you know what the answer is. It's on the web, so you can always double check what you're doing. And it may take you half an hour to do those. That's okay. Go to sleep, relax, go back the next day, redo it. It will take you 25 minutes. Same thing, put it on the side, redo it the day after. Oh, 20 minutes. Keep doing this, and then you will be able to do it in like 5, 10 minutes. Then you know you're ready for any situation. All right. Equilibrium is all power. I just want to suggest on E7. I'm going to leave that to you, but as you work it out, which one is that? Maybe that one. E6 or E7, I forget. E6, oh, E7 is with the position vector. Okay, so you know how to do this. But for this one, the key to this, remember when we apply Newton, we usually pick a massive system. You're looking for the tension here. You're looking for the tension there. And since Newton usually is applied to a massive system, obviously this is going to be a system. So you're going to neglect the inner tension here. And this will have a mass, which is the mass of the block attached. Done. Easy. If you don't do this, then it's okay. You're still going to complete the problem, except you have to apply Newton to this system first, and then apply Newton oddly to this little point. And then you're going to use Newton's third law. Do both methods. Make sure you get the same answer. It's a piece of cake. And then for the other one, E blah blah blah, the only difference is you're not going to be given this. You're going to be given points, right? No problem. This is where you're going to use the unit vector, right? The technique that we've seen, EOB, is the same as ET1. And then EOA is the same as ET2. And you're going to express your vector T1 and T2 in unit vector notation. So you're going to redo the exact same math problem that we've done last Monday. And same for T2. Okay? So it's pretty much a math problem. All right. The next step that I will like to go over is I'm going to skip Atwood, go directly to pulleys, and then I'm going to go back to Atwood. I want to allow you the time to study those stupid Atwood system over the weekend. Okay, so let's take a quick break. And let's go over pulleys. Let me release the board so you can navigate previous boards. Okay. If your pulley is at equilibrium, the tension, the value of the force or the tension along the string is always the same. Therefore, if you apply the tension T here, follow the string, tension is right here. Not here. It's not part of the string. The string goes around the pulley. That's property number 1. Hence, in this pulley, tension along this is the same as the tension along here. And similarly, the tension here is the same all around here. So just follow the string. The tension is the same along the same string. But that's if and only if the pulley is at equilibrium. Very important. If it's not equilibrium, all games are off. And we're going to see that more with that wood. I'm going to change that in chapter 10 or 11 as we do rotation. If the pulley now rotates in such a way that it's being accelerated, two cases. If your pulley is massless, which obviously is idiotic, but when we say that, we only means that the mass of the pulley is so small compared to the forces acting on it or attached to the string. If you can consider a massless pulley, the tension is still the same along the string. So back to what we said at equilibrium. But if the pulley is massive, the tension will be different along the string. Okay? Write that down. Keep it. We're going to revisit this as we start rotation. So, now, why do we care about pulleys? Well, this is why pulleys are so cool. If you have an object of weight W, and you'd like to hold it there with your hand, like that, and then like that. What is the force that your hands need to apply? At least. Excellent, most remember. Let's see how. How they make our work so much easier. If you want to hold that block, and you know the weight is W, what must be the force that your hand must apply on that string to hold that block where it is, at equilibrium? Exactly. You have to apply a force T, and as you apply Newton in your head, trivial, you will end up that T minus W is equal to 0, therefore T must be equal to W. If you like to bring it up, T must be higher. Okay, let's see how most men suggested that pulleys are going to make our life easier. I'm not going to use the word work, because the word work is very misleading. The interpretation of the word work in layman's term is going to be broken in the next 2 chapters. So we're going to redefine it. So I'm not going to use just it. I'm going to replace it by life. How's that? Yeah. Let's see how. Excellent. We're trying to figure out what is the magnitude of T to hold this at equilibrium. So, T is in contact with the pulley, so let's do Newton on the pulley. Let's identify all the forces acting on the pulley. Let's start with the massless pulley, so we can neglect the weight of the pulley. If you have a massive pulley, don't worry, just add the mass, the weight, that's it. So let's do it massless first, just to get the idea. If a force T is along this string is in contact with the pulley right here, and the same string is in contact to the same pulley right there. So there's 2 contacts. Since we're going to use the property of the pulley, which is that if it is at equilibrium, the tension along the string is the same. As we follow the string, if this is T acting up, there must be another T here. That's it. That's the property of the pulley, T and T. As we look at other type of contacts, obviously T is in contact with W, so there is another tension here. This cannot be assumed to be T because it's not along the string. Let's give it another name. Let's call it T prime. All right. Now, obviously, as we do Newton in our head, we end up with 2T is equal to T prime. Is everybody with me as I skip everything? Do we all agree that as we apply Newton on this particular pulley, set up a y-axis vertical, we're going to have T plus T minus T prime is equal to 0, therefore, perfect. Now let's do analysis on the weight, because we want to connect that force T with the weight, and we don't know what T prime is. So let's do Newton on the weight. Again, we're going to have the weight here, and we're going to have a tension. And that's where we realize, hey, look, which law are we going to use right here? At the connection between 2 systems? Excellent, 3rd law. Therefore, we can write right away that this tension up acting on the block is T prime. Therefore, as we apply Newton's law to this, obviously T prime is equal to W. Combine those two buggers and you have T is equal to half the weight. Woohoo! We've just managed to cut down the weight by 2 to hold it where it is with one pulley. While if you don't have a pulley, we would have to apply the force T, which is equal to the weight. So we cut the amount of force that we need to use to hold that block W by half. No, because if I substitute T here, my T prime here, T prime disappears, right? And I end up with 2T is equal to W. Therefore, T is equal to W over 2. No? Are you with me? Or the question is asking what is the relationship between T and W? Yeah, those are always magnitude, right? As soon as you're applying Newton's vector law into your coordinate system, the equation that you write are all scalar equations, right? So therefore they all magnitude. That's why they have to be positive. Okay, perfect. Now look at this little bugger. Let's see what happens if you use 2 pulleys. Let me blow it away. Zoom. Oops. Hey, oh, give me there. Nice and big. Okay, let's follow the string for T. T is here. Let's follow the string. T is here. Therefore, this is a new force. Let's call it T prime. So far, so good. So as we apply Newton to this pulley, 2T is equal to T prime. Stop me if there is anything funky that I'm doing. Alright, now let's use Newton's third law. Newton's third law tells us that if this is T prime, this is T prime. Let's apply the property of the pulley. This must be T prime. The last contact is this little bugger. Don't know what it is. Let's call it T prime prime. Therefore, as we apply Newton's law, we have 2T prime is equal to T prime prime. And now let's do the last one. W. We realize Newton's third law again. That must be T prime prime. Therefore, T prime prime is equal to W. 1, 2, 3 equations, 1 unknown, assuming that we know W. Let's substitute this bugger here. Now 2T prime is equal to W. Therefore, T prime is equal to W divided by 2. Let's substitute this here. Therefore, 2T is equal to W over 2. Hence, T is equal to W over 4. Now we've managed to cut down the weight by 4 by adding 2 pulleys. Okay? That's why pulleys are cool. So all the other P problems are just different configuration of pulleys. So please practice them. Always the same. When you say weight, are you talking about the weight of the pulley or the weight of the block? The block. Yes, but that's beyond the scope of this class. Because then we have to consider the shape of our pulley and where the forces is being distributed on each part of the pulley. For this, you're going to use MATLAB in 300, 400 level. For us, we only consider each object as an individual zero-dimensional point, as we've been doing before. So we won't care too much where exactly the force is applied on which part of the system. Does that make sense? Perfect. So now if you like to redo the same problem with massive pulley, no problem. You just add the weight. Here, let's call this W prime, which means that this equation becomes T prime plus W prime, which means that the final answer will have a stupid W prime that is being tagged along. So as you can see, if you consider massive pulley, you just carry out the weight of the pulley in your equation. No biggie. No biggie, no biggie, no biggie. Okay? So, rule number 1, pulleys. The main property, make sure you write all that down, is that if your pulley is at equilibrium, the tension applied along the string touching your pulley is the same throughout the string. If later on, we're going to see this in Atwood system, your pulley is accelerating, so not only rotating but also accelerating. If we consider a massless pulley, same thing. We will be able to make an assumption that the force are the same on both sides of the string, just to make our life easy at first. Then later on, as we're going to learn about rotation, and specifically angular acceleration, then you're going to lose that assumption, and now the forces along the string is going to be different on each side of the pulley. Okay? And as you're going to take C270, you're going to break the first assumption that we just made, which is that the two tensions are the same. There actually is a relationship between each of those tensions that has to do with an exponential. If I believe, if I recall correctly, it's going to look like this. And this alpha is the angle around the pulley. So in this case, 180. Okay? But we use this in next class. So as you're going to take higher and higher classes, you're going to refine your model. In this class, we always pick a very easy, simple model. We simplify them. And so we make that assumption. The tension is the same along the string if the system is at equilibrium. Next class, you're going to get rid of that stupid assumption and look at real case, take measurements, and you're going to realize, no, they're the same, even in equilibrium. And here is the relationship to this stupid little exponential. No problem. Squeeze it in there. Perfect. So I will leave to you to complete all the P's. So the next topics for this chapter are 4 kinds. First, we're going to do Atwood system. Then we're going to do friction. And as we do friction, we're pretty much going to redo all the previous problems. NA, E, everything with friction. And then we're going to look at specific situation, mainly circular motion. That was a topic in Kinematic 2D, but at that time it was optional. Make sure you read about it and watch the lecture now, because we're going to incorporate it in Newton. And as we learn about circular motion, we're going to apply the circular motion to specifically bank curve. And that's going to be for C people, future C people. Okay? So 3 more topics: Atwood, friction, circular motion, and circular motion will lead us to bank curve. And then before we complete this chapter, we're going to talk about drag force, so at least you've encountered it. But you should have already, because it's on the lectures. Part D, terminal velocity. Okay, so that's where we're going. Questions? So today is Wednesday. By next week, Wednesday, we should be done with Newton, which means we should be done with chapter 5 and chapter 6. So we're going to keep going on energy. All right. Then I think it's time for a quiz. Let me bust it up. Poof. There. What? You're sure you would have to? Yeah. Sorry. Well, yeah, because you know, I had fun running it. I think it's a good quiz. Hey, I'll be here to help. Okay, so I sent it. So you should all have received the quiz link. So I'm going to make several rooms as before, and feel free to move around from room to rooms. Okay, so I'm going to try to group those per topic. Yep, midnight as usual. So I'll be here until 7:30. Then we have office hours from 7:30 to 8:30. So I'll be here too. If you need to go at 7, feel free to go. If you like to stay until 8:30, I work together, feel free to stay. And then I'll bail at 8:30. But if you like to stay until after 8:30 until midnight and keep working with each other, please do so. Or you can take a break and come back after, whatever. This place is always available to you, so use it whenever. Okay, breakup room. Allow participants, yes. Create. Number of room. Let's create 4 for now. Okay, the first room will be Q1 until Q8. Those are mostly definition. And then room 2 will be Q9 until Q13. And then this room will be Q14 until Q15. Oh, okay. Henry decides to go to Q10. Oh, so then only 3 rooms. I'm sorry. You should be able to move yourself, Henry, but I can move you too. Hang on. Oh, I'm sorry. Q10 is broken. Oh, again. What did I do? What did I do? Oh, thank you. Bang, fixed. Oh, I thought I checked that. Thank you, Henry. So please, everybody, reload the page. Okay. Thank you, Henry. Let me tell that to everybody. I'll be right back.